We talk about real privilege, but one of the great things about being here at Duke Law School is, number one, the students. No offense, Nita, but Nita would be the first one who would agree with me on that. But number two, really, is the colleagues, and they've been extremely supportive of me since I've come here last 5 years ago, or almost 6 years now. But among my colleagues, Nita Farahany is really in a class of her own. And she represents I think, the new wave of law school professors, because not only does she have a distinguished legal career, she also, meaning she has her JD, of course, but she also has a master in bioethics and science policy or something like that. And she has, there's a reason I don't have a master's in bioethics and science policy. It's not because I'm writing the Magna Carta this afternoon. But she also has a PhD in philosophy, and she is one of the foremost authorities on bioethics, medical ethics, and she is unbelievably super smart. And what I like about her is every time I talk to her, I know she's like 10 times smarter than I am, but she's always acts like I'm just as smart as she is. And that's really a nice thing for you to do with me, Nita. I think you're going to be very fast. The work that she's done, take a look at the bio in the program. The work that she's done is really some of the most fascinating work being done in the legal, any part of the legal discipline. It is really, really intriguing. And without taking up more time, let me turn it over to Nita. Thank you so much.
Thank you, Charlie. It's always dangerous when in the introduction you're oversold, because then, you know, it's all downhill from there. No, but seriously, it's a great pleasure and honor to be here with all of you, to have an opportunity to talk with you about some of the more frontier issues in national security, so the intersection of neuroscience and national security, which turns out to be a great interest in the U.S. military and worldwide military, is about how can we actually harness everything it is that we're learning about the brain. We are in the era of the brain, and much like in past decades, we were, or really past centuries, we were trying to understand chemical compounds and how they work and how they interact with the body. We're finally getting to the point where we can start to understand the human brain. Now, unfortunately, I'm shorter on time than I would have been if I'd had the opportunity to speak with you yesterday. And so what I've done is I've cut down this presentation a bit, and I want to give you an opportunity to ask me questions and to interact in this dialogue. And so I'd say, unlike what some other panels might look like or other speakers might look like, and waiting until the end to ask questions, just ask your questions along the way and we can talk through it, especially since as a law school professor, I plan to distribute a quiz immediately afterwards to make sure that you actually absorbed all the material. So it's important that you really be awake and alert. But what I'm going to talk about first is to give you the briefest possible primer on the brain and how it is that we're decoding the brain, because that's where the exciting intersection between neuroscience and national security is, and hybrid warfare is being able to decode the human brain. And so figuring out how we can do that and what it is that we can do today to be able to decode the electrical impulses in your brain, but also the different blood flow patterns in your brain, and make sense of that and harness that information to apply it to different techniques and areas. Once you have that brief primer, which squeezes most of neuroscience as an undergraduate education into about 4 minutes, then we're going to go straight into applying the decoded brain. So once we can decode it, what can we do with it? And then there's, of course, the interpretation and applying just literally the decoded brain, but then what about manipulating and changing the brain? Because that is really exciting as well. A few caveats. One is we are not yet at the era of true mind reading. So whatever any of you are thinking right now, I don't know, and I won't know for quite a long time. I suspect that eventually, perhaps in my lifetime, we may get to that point. Not quite literally in real time what you're thinking, but a pretty sophisticated ability to be able to decode your thoughts and the visual imagery in your brain. The second is to say a lot of the things I'm going to talk about today are projects underway, but the military has long been seeking for the ability to be able to decode the human brain, the kind of ability to do mind reading and truth serums. This has been the thing that we've been seeking for millennia, and we haven't gotten there yet, really. And I suspect it's going to be a little while before we can get there in any sort of more meaningful fashion. At the same time, a number of these things are underway right now. So it's important that we be aware and engage in what both the actual facts are, but some of the ethical and legal and broader social implications are of these different technologies. So I'm going to give you two different short snippets to talk you through the two different major techniques. So your thoughts that you think every day, you think about 70,000 thoughts per day. And the way that those thoughts manifest is by neurons firing in your brain. And those neurons that fire in your brain come together in particular patterns that can be decoded. And those particular patterns represent certain things like emotional states, the ability to identify a target, for example, different sophisticated things to different really simplistic things. And those patterns of firing are things that we can pick up with EEG. So that's what the first video will be about. The second one is the more sophisticated technology, but a little bit less relevant for our everyday lives because it isn't portable. It's a giant magnet that you have to go into. So we can learn a lot of interesting things about the brain, but it's not going to show up on any battlefields anytime soon. Okay?
Can we change, and should we change, the traumatic memories that ruin lives? The answers lie in the web of electrical impulses inside your skull. Your brain is an incredible piece of organic machinery that produces something far greater than its component parts. Breakthrough science lets us study those parts as never before, uncovering the hidden processes that form our identities and offering new hope for those with brain disorders.
The brain is an electrical system. That's how we measure the brain activity. The cells communicate by sending electrical pulses to one another.
Okay, so brief thing just to underscore this idea of electrical impulses. Now, the reason that's relevant is up until today, not today, but up until recently, what we would do to measure those electrical impulses required a cap that had somewhere between 50 to 100 and more electrodes that were attached to the cap that you would wear. And that cap required at each and every electrode a gel be applied so that there was contact between the electrode and your scalp. And today, it's just a really simple little headset that's dry, that can work through hair as long as it makes contact in a few different points. And it doesn't give you quite the same reading that one of those caps does. But some of the companies that are developing these technologies and working with militaries across the world have gotten to the point where the dry scalp measures and the dry cap measures are nearly as effective as the other ones. That's a pretty big deal. That means that not only is it something that we can use in real time and decode in real time, it doesn't require the kind of sophisticated technician behind actually using the technology because anybody can simply don one of these devices. In fact, I have a half a dozen of them at home from commercial actors. They're only about $150 for the least sophisticated of them, about $1,000 for the most sophisticated commercial ones. For the research grade ones, we're talking about a couple $1,000s at most. And they're portable, they're lightweight, and they're easily integrated into things like helmets. Okay, so that's one. Two is fMRI. So this is going to be a kind of two-part video where I just want to show you kind of the extraordinary thing that we can do with functional magnetic resonance imaging. So what's neat about EEG is it gives you real-time information about the firing of activity in the brain. A different technique to measure what's happening in the brain is to look at blood flow through the brain. As you have different areas of your brain used for different pieces of information, blood flows into that area of the brain, and then blood leaves that area of the brain. And what happens is that it comes in as oxygenated blood, and it leaves as deoxygenated blood, which means that you can measure that change in oxygenation through a giant magnet. What does that giant magnet look like? It looks like an MRI that many of you may have experienced before, or a CAT scan that you may have experienced before, but a person lying quite still as we have them do a series of tasks. And as they do those series of tasks, being able to pick up the changes in those different regions of the brain. So I'm going to first show you just a quick clip about that concept, and then something that for me still surprises me and gives me chills, which is Jack Gallant's work at UC Berkeley, showing you the decoding of a person's brain while they're watching a video.
Neuroscientists often use brain scanning techniques like functional magnetic resonance imaging to see which areas of the brain are active during tasks. Brain decoding looks inside these active areas to identify more subtle patterns related to particular images or ideas. A typical study would put someone in a scanner and show them a series of pictures. For each picture, the scanner records activity in the areas of the brain responsible for vision. A computer program, the decoder, is then trained to associate each picture with its pattern. To test the decoder, a new picture is presented. The scanner records the activity again. The decoder then compares the new pattern to the pattern it knows from training to figure out what type of object the person was looking at. Some groups have gone further. Jack Gallant's lab at the University of California at Berkeley measured brain activity as their subjects watched hours of movie footage. They taught a computer program to associate the clips with brain activity patterns, as before. Then, the decoder reconstructed what the subject had seen. Based on the brain activity alone, the computer sifted through lots of video clips and produced an average, here on the right, a best guess that it thought was most similar to what the subject had seen. Decoding what people see is one thing, but how about their thoughts, or even their dreams? Here's a representation of someone's dream, decoded from his or her brain activity. It's from Yukiyasu Kamitani's lab in Kyoto, Japan. His team got people to fall asleep in a brain scanner and then woke them up periodically and asked them what they were dreaming about. They noted down the most popular categories of object appearing in the dreams. They showed the same participants pictures of these objects when they were awake and scanned their brains again. Then they could tell what was appearing in the dreams, producing depictions like this, which make about as much sense as dreams usually do.
So this, from my perspective, is really extraordinary technology. You know, what we're doing is we're bringing together computer science with neuroscience. And, you know, these images are kind of blurry from Jack Gallant's lab, looking at what's happening here. So the video clip that they're seeing on the top is, what they're actually watching while they're in the scanner. And then the guess is what is over here on S1, S2, and S3. And you might think, well, that doesn't make me too nervous because, I mean, you can't really tell what I'm thinking from that, except you should know this was just a proof of concept, which means that what they did was they looked in the visual cortex, the area of your brain that represents visual imagery, and they went back just a few layers because there are many different parts of the visual cortex. Some of them have to do with things like color, blurriness, edge lines, things like that. And they didn't decode those areas of the brain in this paper, which was 4 years ago. Instead, they just went back the first 3 levels. And so the fact that they got the kind of representation that they did from decoding the brain is pretty extraordinary. Jack Gallant's lab has done the same thing now with language. So they've read people's stories, and they have had the computer trained on what the blood oxygenation level looks like as people have read stories. They then read news stories that the computer doesn't get to see, so it doesn't know literally what it is. It's some novel kind of story, and the computer has to predict what it is that the person is hearing, and it's pretty eerily accurate. Not perfectly accurate. I mean, we're talking about 80 to 80% accuracy right now, but 70 to 80% accuracy of decoding your brain is pretty extraordinary. That's pretty amazing stuff. So this is where we are today. Where we are today is trying to take all of these complex patterns that occur in the brain, from electrical activity that occurs in the brain to blood oxygenation level coming into and leaving different regions of the brain, training computers on what that information means, and coming up with essentially a brain dictionary. How can we decode what happens in different regions of the brain? And it's distributed. You can have motor regions of the brain, so you may be having thoughts like, how do I move my hand? To other thoughts like, here's where I've hidden a bomb that might be interesting for you to know. Right now, when it comes to fMRI, it requires a willing and cooperative participant. It's very easy to basically fool the machine. Now, not while you're sleeping, if your dreams are being decoded, and if you're put to sleep in order to gather that information, then it's actually quite easy to take the information from your brain by putting you into a scanner. But if you're in the scanner and you're awake, all you have to do is think of like a pink elephant and just keep thinking about the pink elephant over and over again. And the only thing that's going to show up is the pink elephant or some representation like it. We've tried with different drugs and things like that to see if that could somehow enable us to decode what's happening in conscious thought or what's happening in the visual cortex. It's very difficult without a cooperative witness. Okay, so now that you all have fully in your grasp how the brain works, blood oxygenation level and electrical impulses, we're going to talk about some of the applications of that. And the primary applications that we're going to really focus on are some of the electrical ones rather than the fMRI ones, but keep the fMRI ones in the back of your mind, because what those are doing is not so much coming up with portable technologies that we're using out on the fields or portable technologies that we're developing for military purposes. It's decoding the brain so that we know how to make sense of the brain. So when we start to decode what the electrical activity in the brain looks like, when we start to make sense of that, a lot of that research is coming from fMRI. All right, quick check. Any questions about any of that? Yes. They're not. They are different, although the representation of animal appears to be the same. So semantic representations appear to be the same, even cross-culturally. But you have subtle variations between brains, which can matter. So the fact that it's different, just to give you a quick example in response to your question, one of the technologies and applications that we've been talking about is the ability to use your unique brain signal, the fact that your pink elephant is different than my pink elephant, to make your brain the ultimate passcode. So it turns out if you wear one of these EEG devices, which communicate via Bluetooth to your telephone or your computer, the way you think about pink elephant or the way that you do a math problem, even the same math problem, or the way you sing a little ditty in your head, will have slight variations in representation, slight enough that your neural signature could be used as the best authenticator of who you are to be able to unlock your computer, to unlock your phone, much more secure than other mediums that we've been using. So people have been developing these technologies as a way to have a kind of uniqueness. It's not so different that we can't semantically decode it, but it is different enough that it can be used as a unique neural signature. Any other questions? Yes.
I have a question on intent.
Yes.
So let's assume you can imagine an elephant. We know you're thinking about an elephant. Do you foresee a way in the future where you'll actually be able to determine the intent of the actor? Okay, I see an elephant, I want to run away. Because in the law of war, intent is critical.
Yes. Yes and no, right? So again, what we need for intent is you need real-time intent decoding, and EEG is the most promising for that. It takes the amount of information it takes to decode through fMRI signals is hours of information, but intent translates to emotive thoughts, and those emotive thoughts are things like a quick state of arousal, the activation in your motor cortex, even when you're not running, when you're thinking about running, you see activity in the motor cortex. And we're going to talk about threat detection in a couple of minutes, where you'll see we're harnessing some of the instantaneous emotive reactions that arise during threat detection to be able to improve threat detection, but also be able to share the most skilled person in a group, their information if they have a helmet on and everybody else does. You can send that sense to everybody else so that everybody else instantly is on alert as well. So we can pick up rough forms of intent, not literal intent, not the thought, I want to run away, but the associations and emotive associations that come along with it. Yes?
I realized you weren't here yesterday. We spoke a lot about the issues with cell phone privacy and stuff.
Yes.
How are you guys, how is the industry going to handle the ethical?
It's really problematic.
Yeah.
I mean, it's really, really problematic.
Now you're invading the only thing we have left, it feels like.
Yes. So I'm writing a book right now called On Cognitive Liberty. And I mean, it's the last bastion of freedom. What you've got in your thoughts and in your brain, I mean, that's it. That's your final frontier of privacy, and it's pretty much gone. It's toast. So, what I'd say is we are approaching a world of total transparency, and we're going to need to find a very different way to relate to one another. And those little white lies that you tell your spouse, I mean, it's problematic. It's really problematic. Imagine if you had a truthful conversation every day of your life, like, yeah, that dress really does make you look fat. Like, I mean, you can't do that, right? I mean, it's bad. So I mean, it has a lot of implications, including, what about dissident thinkers and, regimes where that dissident thought is the ability to be able to, respond, to react. What about this kind of concept of freedom of thought as a kind of linchpin of democracy? What are we going to do about that? So right now, we're not at the point where I can real-time decode what you're thinking. But just like the past thought example that I gave you, there's a lot of reasons to think that we will voluntarily adopt some of these technologies. And in the military, you might not have a choice, right? I mean, if it's, part of what's considered your health, right? And under the Uniform Code of Military Justice, if you're, required to do whatever health interventions that are necessary to improve your health, and this is considered to be one of them, you might not have a right to refuse in that context, in which case, maybe, within the military context, there isn't such a thing as mental privacy or freedom of thought, and maybe that's something that's, only a civilian concept, and then it starts to break down when we start using it for past thoughts, or the epileptic who wants to use it, or the kid who thinks it's a lot faster to game using their headset, because you can use it it's faster, to do threat detection with your headset that recognizes threats more quickly than you can verbalize it, or than you can operate a joystick. So there's lots of reasons why we will uptake these things, just like there's lots of reasons why we give up our privacy every day. And this is it. This is our last bastion of privacy, I think. And it's almost over. All right? I'm here for your happy dose of morning coffee, right? All right. So, just to give you a sense of what is it that we're doing with this. Well, a lot of technology in neuroscience, just like in any other area that's developed, starts with some application that then has a dual use implication to it as well. And one of the great hopes and promises of this EEG, harnessing EEG technology, you can see this is the kind of skull cap that I was talking about, which is far more cumbersome than somebody would wear on any ordinary basis. But this is a research team at the University of Houston created an algorithm, because remember, this is computer science coming together with neuroscience, that allowed a man to grasp a bottle with a prosthetic hand powered only by his thoughts. So imagine that kind of manipulation, to be able to open and close, grasp a bottle. That requires some serious dexterity, and to be able to drink that bottle. And why this was so amazing is, up until this happened this past year, we thought that the kinds of chips that you have to invasively implant into the brain, which I'll show you in a few minutes, was the only way that we'd be able to get the kind of signals that we needed to be able to operate things like a prosthetic hand. And in the military, that's amazing if you can actually restore function just by thought-controlled prosthetics for the number of people who come back with some sort of injury, losing a limb, losing a hand, losing a leg. To have that, the ability to manipulate the external world through finger gestures, digital dexterity, is pretty extraordinary. And to be able to do it through a simple cap that you wear on your head rather than a dangerous and invasive therapy is really amazing. So that's one of the promises, and the Defense Advanced Research Projects Agency is investing a huge amount of money into the development of the ability to manipulate neuroscience to enable prosthetic use, right? So that's great. Now, the dual use of it, of course, is that then we can control robots, right? So instead of just being able to control a hand, what if you could actually control an exoskeleton? What if you could control a combatant that's in the field? So China has been training students at a military academy to use headsets that detect and interpret the brain activity of the wearer, allowing them to control machines. And this you see actually in one of their military academies training the students to be able to do so. And at the demonstration at the People's Liberation Army, Information Engineering University, the student used the device to send the robots trundling in different directions, just one of these little skull caps, and just powering it through thought. That's pretty amazing. We've done this in animals where thousands of miles away, we've been able to take primates, train them on being able to move a robot, and have the robot operate, walk on a treadmill thousands of miles away just by watching it via video camera in real-time Skype, which means you don't have to be literally watching it right here to operate the robot. Now, surely that is just self-evident what some of the implications of this are, right? So if you can start to have that kind of ability to sit somewhere comfortably in a protected area while you operate robots in the field, that's extraordinary. Now, this uses EEG. It trains the computer to recognize particular patterns that accompany the commands. And right now, the technology requires a great deal of concentration to really make work, to even do simple tasks. And it's only about 80% effective in translation of what you're thinking to actually getting the robot to operate. And so it's a really interesting concept, but we're not there yet. And it's much slower and much less accurate than just being a combatant in the field right now. But the promise and the potential is pretty enormous. If we're already at the point where we can grasp a hand and then we can do it remotely by operating a robot, this obviously has huge military potential. And while I give you an example of it being used in China, the Defense Advanced Research Projects Agency is investing a huge amount of money in trying to do it here. And there are a number of examples of US researchers who are also doing it. So this has extraordinary and really promising potential, but also some frightening potential if you think about the changing nature of war. And just like we can do it for robots, of course we can do it for drones as well.
It's amazing what you can do if you put your mind to it, like fly a drone, for example. I've come to an airstrip on the outskirts of Lisbon, Portugal, to see some groundbreaking technology in action. This is Nuno. He's controlling the drone that's whirring away above our heads using just his brainwaves, all thanks to the skull cap that is constantly monitoring his brain for activity. It's a slightly unsettling demo as the drone buzzes up in the sky, struggling valiantly against the wind. It's the first time this has been shown off in public, but if the researchers here get their way, it's the starting point to something much, much bigger. So this is quite literally some blue sky thinking. The researchers here say that this technology could eventually be used to power even commercial flights around the world, removing the need to even have a pilot. Now that may seem a little far-fetched, but didn't we once say that about driverless cars?
It's where it's going, right? Technology is evolving, the regulations are evolving, and so it's both things are going at the same time, and we're learning with the technology, and the technology is learning from the possibilities. So it's obvious that it's going to happen. The question is not if, it's when.
The prospect of travellers being happy to get onto a plane without a pilot is probably a step too far, at least for the next few generations. But the dream here at Drone Maker Tech Ever is that brain-powered technology could in the short term enable those with disabilities to control aircraft.
So that's one possibility, which is individuals with disabilities can control aircraft. But to give you a sense of where this is going, because you might be thinking, well, why would we have somebody, a drone, why not just do it, right? I mean, just operate it manually. And the idea is not just that we're going to get to the point where you can do it through thought. The idea is actually that we're training the machines to understand thought. Right? So the purpose is for machine learning, to take neuroscience and be able to translate it into artificial intelligence. And in fact, that's what we're doing in part with threat detection. So the very best people at recognizing threats quickly and scanning through hundreds of thousands of images can't verbalize how. They can't literally explain to you what it is that triggers them to be able to quickly and efficiently identify a threat. But they can do so. They're able to do so more efficiently than anybody else, and part of it has a brain signal. and it has an electrical brain signal. In part, one of the brain signals is called a P300 signal in the brain, which we can pick up through EEG. And so there have been a number of different programs. One of them currently underway is called the Neurotechnology for Intelligence Analysts and the Cognitive Technology Threat Warning System, where what we do is we try to non-invasively record threat target detection brain signals to improve the efficiency of imagery analysis and real-time threat detection, respectively. And by picking up those signals, you can then train the computer and develop computer algorithms to figure out what is it that associates the kind of signal with the particular thing. So you're looking at thousands of different images, you pick up what it is, that starts to enable the machine, through machine learning, to develop an algorithm to see which things are threats and which things aren't. It's much harder to code and say, here are the characteristics about a particular image that make it threatening. It's much easier, it turns out, to train a computer to identify threats by being able to associate this is a threat, figure out what it is about it that is a threat. And so the result has been, through sophisticated EEG training of the very best threat detectors on computer algorithms, we already are at the point of being able to have AI more efficiently, in some instances, sift through these thousands of different photographs and to be able to more efficiently identify threats that are targets for military intervention, military response, etc. That's pretty extraordinary that we're already there to be able to translate neuroscience into AI. And it means that the more we learn about the brain, the more we're able to take these computer algorithms and turn them into machine learning, the less we necessarily need individuals sitting in front of and recognizing the different images and the different targets. It also means we can much more quickly sift through hundreds of thousands of photographs, hundreds of thousands of satellite images to identify and respond to targets. Questions about this before we move on? Yes?
So this is 3 steps ahead already, but both with the individual who's skilled at threat detection or the artificial intelligence, are we thinking about how easy it is to deceive those two things?
Yes. So that's part of manipulation, right? Which is, it turns out that not only can you, this is all one way rather than two way. So one is, how can you train the systems inaccurately, right? How can you give a lot of false positives so that you can undermine AI systems that are developed by us, by other countries? We're not quite there yet because we're just at the point of doing threat detection, but that's one of the things that people have to start recognizing is there's always a countermeasure. And the countermeasure is something that you have to start to anticipate and be able to address. But the second, which we'll talk about when we get to manipulation, is you can implant thoughts, you can implant memories, you can implant and deceive by actually changing a person's brain. So what we've been talking about is detecting rather than two-way technology, but we're already adopting two-way technology that isn't just picking up electrical impulses, but also sending precise electrical impulses that change a person's brain. Other questions? Yes?
This goes back to a couple slides ago. It's about the problem of attributing the thoughts. So if a robot acts and it does an unlawful act, is there technology built into those helmets that would prevent us from figuring out the identity of who ordered the robot to act? Just like your comment about the signatures
right.
makes me think of this.
Yes and no, because once you digitize something, you can mimic it. Right, so it's possible to hack. It's possible to mimic. It's possible to send signals. If you can break into the system that is sending the commands to robots, can you change what the commands are? Yes, you could change what the commands are. Could you pick up the signals and figure out whose neural signature it is? Just like your DNA is a unique fingerprint, we can start to actually identify neural signatures with particular people and particular actors. And one more interesting thing is it turns out that we can start to identify language processing as different neural signatures in the brain. So the Chinese native speaker and the Arabic native speaker and the English native speaker look a little bit different in how they process language and information and commands. And that might tell us something about the identities of the individuals as well. So there's a lot of rich information here that we don't have adequate security around yet. So one of the problems of deploying some of this is the problems of the kind of information intelligence that we're sharing by starting to put this information and digitize it and put it into machines and out into the ability to kind of be hacked and tapped into. Other questions? Yes.
Thanks so much. This is really interesting. My question builds on that a little bit. As I was watching the examples of the people thinking and making a robot or a drone do something, what if a person is distracted by something?
Yeah.
So, I mean, I'm picturing that, kid getting the drone. I'm imagining sweat pouring down as he's trying to think only about the drone. How do you?
Yeah, it requires an
account for
extraordinary amount of concentration right now. Yeah, it'd be bad, which is like, oh, wow, I'm hungry, crash, right? I mean, that's a problem, right?
Goes, to the next piece of that is if you think about this in application to
Yes.
making threat decisions or decisions to act, how does this kind of system account for someone saying, God, I wish we could just kill that guy, but then not sending that message, but sending the message of, well, we can't, so we're going to do this instead?
Yeah, great questions, not yet fully addressed. I'd say a couple of things. One is some of the ideas of this is to actually take out the person from the equation, right? So with self-driving cars, it's not having a human actually do it. It's training on a human to understand what human reactions are and being able to use that for machine learning purposes to then have AI do it. And so once you take the human out of the equation, you're much less likely to have those problems. You're also much less likely to have some of the safeguards that come with human inhibitions and natural evolutionary responses to situations that might be difficult to program. So we have a lot of AI learning to do to be able to pick up both the natural inhibitions that lead us to not actually do things, and a lot of override systems that you need to have before you really feel comfortable delegating decision-making, target identification, or target elimination to AI, right? You might allow faster target identification, but at this point, you certainly wouldn't want to have responses automated. You'd want to actually have a human involved in the decision-making process before we get to that point. But eventually, could we get there? We're getting there with driverless cars. And there's no reason to believe we wouldn't get there in this context as well. All right, just to close out this piece of it. Well, I don't want to take up your break, but I will continue. Wow. You never take away a morning break from people, but I may bleed in 5 minutes into your break. But just to say, this isn't just threat detection for purposes of training AI. So this is kind of a futuristic helmet, but it's not that futuristic because we're already testing it in the field, which is to see if we can pick up real-time EEG data from people who are in the field. And can we embed that information into headsets? This already has civilian applications. Jaguar has already started to integrate EEG into their headsets for drivers, with the reason that you can actually pick up drowsiness while driving through unique neural signatures showing that you're drowsy. Now, Jaguar hasn't then gone to the next step, which is to give you a little zap to wake you up. You could do that, but instead what they're doing is giving you a little alert that says, like, hey, you might want to pull over and have some coffee. I don't think people would be buying their Jaguars if they had the opposite option, but we could do that in combatants' helmets. And you could imagine that this is quite important and relevant for something like Air Force pilots, people who are operating machinery. You don't want them to be drowsy. You want them to be quite alert. But what's neat is the threat detection that some people are so good at, you can have sense sharing. So one person alerts, you can actually send a signal out to everybody else who experiences the threat detection warning before they could consciously process it themselves, which means without having to communicate it verbally, you could share basically like telepathically, right? But not having to do it telepathically because you're sending an electrical signal to everybody else in the unit at the same time. And this isn't just threat detection. The ability to be able to share simple commands and other information through sharing this rather than verbal commands hasn't yet been accurately detected, decoded, and it's much harder in the field to detect and decode that information, at least today. But if we get to the point where brain decoding is just as easy as verbal decoding, this won't be that much of an advance. Right now, it's a significant advance. Yes?
As far as threat, like the way I experience threat may not be experienced the same way as somebody else, just like my interpretation of threat may not be interpreted.
Oh, but it is. It is. I mean, it is different, but it's very similar. I mean, the areas of your brain that are activated are quite similar. The basic responses, perspiration, heart rate increase, the kind of areas of your brain that are activated, it'll be a little different, but it's really quite similar across brains. So there is variation between brains. We're having to do this across thousands and thousands of individuals to get to an accurate brain dictionary. It's still going to have some variability that isn't going to be perfect, but it's much more predictive than you might think.
Mm-hmm. There's a huge difference between military and civilian in interpretations of threat.
Yes.
So military.
Well, and so we're doing this in the military context, right? I mean, this isn't like taking civilian technology and applying it in the military tech. This is looking at real, actual threats or real-time, combatant information, real-time, kind of information that we're gleaning from the field. It's that kind of stuff that we're using to train this information in the military context. And then we'll get to the civilian context where, you're scared because you're watching a movie. We're doing that too. Nielsen has a huge EEG program, and a lot of different film developers are using that information to be able to make sure that they have a really scary Halloween 14, right? And figuring out which scenes activate different emotional responses in individuals to be able to have the best possible trailer to sell their movies.
EEG core signals are the same regardless of how it's interpreted.
Basically, right? I mean, so they're waves. So what you have is brain waves. And those brain waves are within bands and frequencies. And so you might be at 12 hertz and I might be at 10 hertz when we're experiencing an alpha wave, but we're in the same band. And so it doesn't have to be so specific that it is at exactly the same frequency. It's bands of frequencies that we're able to get better and better at interpreting that actually interpret the emotive state that we're experiencing. Yes?
Does the intensity of physical stimulus matter? For example, if you're witnessing a gunfight and there's lots of multiple threats as opposed to one single shooter over there in the...
It's a great question. And so the question is, how much does the intensity of the emotional stimulus matter, or the physical stimulus matter? We don't know fully yet. So part of it is deciphering and decoding pain, whether it's emotional pain or physical pain, is something that just in the past few years, we've actually been able to see and disaggregate what that information is, and being able to measure intensity of pain or intensity of emotional reaction to things. So it matters. And we're getting to the point of being able to measure and understand that. It depends on the context for how much it matters for what it is that you're asking. But we are starting to recognize that it's not just pain, it is intensity, duration, kind that we need to be able to disaggregate. Yes?
Yeah, let's wait for the microphone so the people in the overflow can hear.
Okay.
Are you saying that you are capable of sharing information that I'm experiencing some kind of experience, or are you saying that by sharing it, we're trying to manipulate others to have the same experience?
Certainly the former, maybe the latter. When it's one way and just sharing, you're not trying to manipulate, you're trying to share. But sharing might lead to a person experiencing fear, or might lead to a person experiencing the same kinds of emotional reactions and physical reaction that the person who experienced the threat detection did, right? So the person who is most quickly and most efficiently able to do threat and target identification experiences heart rate increases, experiences arousal and alertness, a kind of shot of adrenaline into the system. And by sharing that information much more quickly than you could verbally share it with somebody else, the other people are going to experience that as well. I'm not talking about shocking somebody with electrical activity and changing their brain. I'm talking about sharing information which might lead to a state of arousal. All right, we've already talked about the kind of spy implications. I see a question back there.
Yes, ma'am. So you talked about the ability to sort of share this general sense that there's a threat or general sort of threat detection, but it strikes me when we're talking about hybrid warfare in and among civilian population, urban environments, coin fights and things, a degree of specificity that would really easily be communicated by explicit verbal communication would be beneficial, as opposed to maybe just putting everybody on sort of this general threat alert in a situation where not everybody else is as skilled or as proficient at identifying the threat as the person who initially does.
So it's not mutually exclusive, right? More quickly than you could actually say, whatever the coordinates are, or however it is that you would actually communicate a threat, for people to be on alert faster than you could communicate that is useful. And then the specificity, you're right, you're going to need much more specificity in communication. And so I'm not suggesting we're only going to communicate via sense sharing, but sense sharing can enhance the experience and the ability to actually put people on the kind of alert that they need to be on and the readiness that they need to be on. And the more specific we get on brain decoding, the more accurately you could actually share the information. It can be translated verbally as well into helmets, just as it can be translated through a kind of state of arousal or high alert or something like that. So hybrid doesn't mean we replace one with the other. It means we enhance the experience that we're experiencing right now. Yes?
Hang on a second. Hang on.
I understand you're talking about it coming out of one brain and becoming a digital signal. How does that digital signal get into the other brain? Is it just the same kind of exchange?
It doesn't have to go into the brain. It can go into the helmet, first of all, right? I mean, so for example, you could have a red light that goes off, right? I mean, you can do things like that. For us to literally translate it into the brain would require either that it requires a two-way communication rather than a one-way. One way is EEG picking up the signal. Two-way is using something like transcranial direct current stimulation, which signals in the right area of the brain the information, or using implanted electrodes, which we've been talking about as well, which would transfer far more precise information, far more specific information, and maybe a high degree of specificity of information as well. Yes?
Please wait for the microphone.
I'm going to repeat it, which is how much does it matter? I mean, how do you do it with more than one person?
Right.
So if multiple people are identifying something at the same time, does everybody get the signal out?
Right.
So you could, you can just control for this, right? Which is, suppose you really do have a person who is the person who is your target identifier, or the person who's the head of the unit, the, command. Whoever it is, you can designate a person who is actually transferring the information, or you can figure out a way that actually you have multiple people being able to share information at the same time. And so this is some of the stuff that they're trying to work out is what the logistics of it are, and the logistics are going to depend on the context of the situation and what it is that we actually think we can do with brain decoding and how valuable it actually is. Yeah.
So I don't understand. What is there a geographic limit to how far this
the communication can occur?
Yes, yeah. And
not necessarily. I mean, there's no reason why that's not a matter of neuroscience. That's a matter of your technology, right? So if you can transfer information from the field back to any other place on Earth, you can do that just as you can with this signal as well. So it shouldn't, that's not a neuroscience limitation, that's a technology of communication limitation.
And what about if you're communicating this threat that you observe and the person or the people you're communicating it to don't believe you? Then what happens?
So I think we need to get to the point where we have much greater specificity and comfort with neuroscience and training so that we all feel like that's a threat or a communication that's credible. And then I'd say that's no different than any other context, right? So if you have somebody who verbally says, hey, I see a threat at, XY coordinate, and that's a person who cries wolf all the time, and the rest of the people in the unit actually think that's a person who cries wolf all the time, having their brain tell them that as opposed to their verbal commands tell them that isn't going to make a difference. So, you need to have a person who's reliable, who other people trust in order for the signal to be reliable and for other people to trust it. But also we need to show, just like, with driverless cars, we need to be sure that the driverless cars are actually better than humans behind the wheel and that we don't end up with more accidents and that we don't end up with more problems. We need to show that reliance on neuroscience is in fact more effective before we actually deploy it in the field. And so I think once people have that degree of comfort and a reliable person, then you can rely upon the information that they're sharing. Yes.
So I'd like to ask, excuse me, a question moving it back into the medical applications. You showed EEG relative to prosthetics.
Right.
And I also think that I understand that DARPA, who's sponsoring this, is also doing a lot more in the medical area.
We're doing a lot
So
in the medical area.
is there a connection, if you could explain it, with the potential for EEG or fMRI relative to understanding the root causes of PTSD and tinnitus and some of the battlefield injuries that we've seen in the recent 12 years?
Yes, that's some of, so I'm going to say we're not going to do changing of the brain given the kind of time limitations that we have. But one of the things that's really promising is for PTSD purposes. And this is changing the brain, right? So it's not just detection, but actually literally changing the experience that a person has. And it turns out there are a number of new advances in neuroscience that enable us to overcome depression. It turns out through precise kinds of stimulation of the brain that might be a much more effective treatment for PTSD and for disaggregation of memory. A big area of research for DARPA and a big area of research for a lot of the investment in neuroscience is being able to understand memory and how you can affect memory, how you can enhance memory, how you can restore memory, but also how you can disrupt the emotional valence of a memory from the semantic content of the memory. PTSD is really the reliving of the emotional experience together with the semantic content of the memory. And if you can reactivate the information, so the way memory occurs is it's sort of like RAM in your computer. Memory exists in RAM in your computer, and then it gets stored in kind of long-term memory. And every time you recall it in RAM, it's a little unstable, and it can be changed and manipulated. And so if you can reactivate the memory before it's reconsolidated, and then you can change it, disrupt it, disaggregate the emotional content from the semantic content, and then have the semantic content, for example, stored if you want to keep and preserve the memory itself, but degrade the emotional content so that the memory fades just like any other memory fades. That can be quite powerful for improving the condition of PTSD, overcoming PTSD, or preventing it to begin with. Even drugs like propranolol, which some of you may take, it's a simple beta blocker that's used for heart conditions, can prophylactically be used to prevent PTSD because it turns out that it numbs you in some ways from the emotional experience, which has implications because if you think about somebody being numbed to the emotional experience, some inhibitions are really powerful and useful for preventing us from doing horrific things. But it can prevent some of the worst kind of instances of PTSD and the worst kinds of experiences of PTSD. So absolutely, there is a huge investment in the medical side, a huge investment in improving the lives of veterans. But DARPA is designed to help us with strategic advantage, not to help us just for the medical applications. And so if DARPA is investing in it, it's almost always for its strategic potential, and the fact that it has a huge additional medical benefit is an extraordinary and wonderful thing, but we shouldn't be deceived to think that that's the only reason with which we're actually exploring that. And if you look at the BRAIN initiative, which President Obama announced, which set aside $100 million for understanding the brain and better being able to harness the information in the brain, by far the biggest investor in neuroscience across every kind of part of the government is DARPA. And DARPA's investment in neuroscience is extraordinary, and they're putting a huge amount of money into it. NIH is up there in being able to understand the health implications of neuroscience, but we're really trying to understand the brain to better be able to use it for strategic purposes as well.
Would I be correct in understanding that the potential exists for two things? One, interrogation law could be changed very, very dramatically. And secondly, turning adversaries, could you turn them from being an adversary to being a friend? Is that on the horizon or theoretically possible?
Yes. So how many of you know what oxytocin is? Yeah, you all experience oxytocin. It's the cuddle hormone. And you don't generally want to be cuddling with your adversary. But if it turns out oxytocin is the hormone that your body releases when you experience bonding, when you experience love, when you experience orgasm, when a woman is breastfeeding. Part of the reason that she continues breastfeeding isn't just the health of the child, it's the huge amount of oxytocin that she gets as feedback as well. So that hormone, the love hormone, may be incredibly useful, and there's been a huge amount of research that's gone into it, and there's some evidence to suggest it can both increase bonding and trust within a unit, which is really important and incredibly valuable, but it might also lead to greater trust in an interrogation setting. If you could actually give it to the person who's being interrogated, they may come to bond and better trust the person who's interrogating them and more willing to share information with them. And you can lead to such great bonding and such great experiences that you might actually, in fact, turn the person. And you can also do that through modifying memory as well. I'll leave it there since I know I've already stolen a good bit of your time with from your break. But
this is such a tremendous introduction to our next panel, which is on autonomous weapons. Look, if you don't mind, could you take maybe one or two more questions?
Sure, of course. I'm happy to take questions. And I'd say if anybody wants to go and have your coffee, I'm not going to be offended at this point since I'm taking away some of your break, but I'm happy to take questions as long as people want to ask them.
One more then.
Sure.
And then we'll take our break.
Thank you. Just going back to decoding the brain, is it also going in the direction of being able to determine whether someone did a certain motor activity, like pulled the trigger, type certain digits into a computer, something like that?
Yes. So, I mean, part of, being able to move that hand is really about motor. So every area of your brain, I mean, so you're not thinking, let me put one foot in front of the other to walk. You're not thinking, let me take the gun and pull the trigger. It becomes automatic. But a lot of that, if not most of it, is happening in your motor cortex. And decoding the motor cortex is a huge area of decoding that we're trying to do, in part to drive prosthetics, but also in part to be able to drive, the kind of external world around you. The only way that you'd actually be able to manipulate a robot, manipulate a hand, have the hand not just grasp a can of Coke, but also pull the trigger of a gun, is to be able to decode what that information means. And so a lot of the work, particularly on the health side, that's seeking to be able to enable people to have an exoskeleton if they're disabled, have a prosthetic arm or device, is to be able to understand the precise motor activity and decode it into very specific commands.
Nita, thank you so much.
Thank you all.